I'm going to talk to you about how computers have evolved over the last 40 years. I'll start with introducing where I joined the computing timeline. I'll talk a little bit about the way that the scale and the cost of computing has changed over time. I'll tell you about the first processor design that I worked on, how it was when we were designing it, and what it is like now. And then I'll finish by introducing a few of the design concepts and briefly touching on how some of the trade-offs in a design change over time. So this is the first computer that I used, a big desk. It's a Hewlett-Packard HP 250 mini computer, and in the 70s this sold for about £15,000. The way that I got to play with it is my dad was selling these. I've still got the book that I taught myself BASIC from, and I was about 8 at the time. The first computer that I owned myself was a Commodore 64, one of the many 8-bit computers at the time. Cost me about £200, and in today's money that would be about £500. And as I was going through this presentation, it occurred to me that the device down the bottom may not be very familiar to a lot of people. This is a cassette player that was used as the permanent storage device. So it would store data as audio tones on the cassette. And even though the memory is quite small, it would still take quite a long time to load a big game that took up the whole of the memory. So my first job, as Paul said, was in radio design. I worked with a design consultancy. I started working on a technology demonstrator for last mile internet access over radio. And this was quite a complicated project with microwave radio front end, 2.5 gigahertz, FPGAs to do the signal processing, and then back-end software control. And as well as working on the radio side, I later did some modeling of some problems that they had with the adaptive filter that was implemented in FPGA. And it was the problem manifested as with a very weak signal. It would think that the noise that it was picking up was a signal, and it would try and tune into the signal, and everything would stop working. And in this company, the projects were typically a few weeks, a few months, 1 or 2 people. So fairly small projects, fairly quick turnaround, building prototypes, helping people with kind of demonstrators and proof of concept. Very varied work. I spent about 4 weekends in a factory in Oldham, supervising a small production run of some of the first remote gas meter reading devices. So that was the first 5 years. Then I moved on to another radio company that didn't go so well, and then I decided that I would try and switch into digital design. So I moved from one black art to what at the time was another fairly niche area. There was very little digital design going on. People would use discrete gates in circuits for small things, but they didn't really between that and using a computer, it was very difficult to access the technology that went into building an ASIC and building a new computer. So ARM was the obvious place for me to work, being as I was based in Cambridge, but I had a very interesting interview experience because I had none of the standard digital background. So when they asked me how to build an adder out of logic gates, I had to think about how to do that from first principles, but it didn't challenge me too much. So They seemed to think that I was good enough for the job. So stepping back from that a little bit, here's some pictures that are mostly taken from a book that my uncle has written on the ever-shrinking transistor, and a few pictures from Bletchley Park. So starting off with valves, I've got a couple of valves here. So here's a large power valve. It's about 50-watt RF device, and this is a more typical logic type of device. So this is equivalent to 2 transistors, just to give you an idea of the size of things before transistors and integrated circuits started to become a thing. By the 70s, the computer that was in the first device that I owned had been designed and built, and I have not exactly the same processor here, but there's a Z80 processor on this board that's the same size, just to give you an idea of what these pictures actually scale up to. So at that point, you could fit a whole computer onto a chip, and it became sort of something you could build into a device that somebody could have in their home. Storage was still quite a challenge. So you can see this picture on the bottom right. That's my aunt standing next to the disk out of a huge old hard drive. That drive probably holds about as much data as a modern CD. Not that long ago, we were using CDs as the way that we would store data to move it from one computer to another. And now a flash drive has improved on the capacity of that by probably a couple of orders of magnitude, and kind of a similar price now to what you'd pay for a pack of CDs in the old days. That would be write once CDs. You could get rewritable ones, but they would be more expensive and slower. And then looking at the cost of these computers, starting the first kind of portable computer probably would be maybe the Apollo guidance computer. That used just over half of America's integrated circuit production for, I think it was a year. And the memory, the program memory for that was actually physically woven into noughts and ones to program the device. So that was a very specialist piece of hardware and phenomenally expensive. Fast forward to the early 80s, the computer that I bought first, roughly £500-600 in today's money. Similar sort of performance, running at 1 megahertz, 8-bit processor, not a huge amount of memory in it, and not particularly efficient for the speed it was running at. The equivalent today in terms of processing power would be something like I've got a tiny little thing here. This is the same as the photo on the slide. So that's a 32-bit processor running at 166 megahertz, and it's mostly a Wi-Fi device. So this is a little radio as a standalone device with a port to connect to something else if you wanted to. And this has got quite a lot more memory than the computer that I had 40 years ago, and the price is far lower. So these retail for a couple of pounds roughly. If you want something a little bit more powerful than this, because this is a very small computer, if you want an unlimited amount of compute power, so the sort of thing that I use every week at work, You can buy that online for maybe a penny an hour per machine. And for a week of my work, to support the work that I do, I may be between the 2 or 3 people in my team, we use maybe £100 worth of computing over a week. So the cost of having accessible compute has almost vanished to nothing over the last 40 years. The price that you would pay for a PC nowadays is roughly similar to what I paid for my first computer, but the amount of compute power that you get has increased hugely. So one of the other things that has changed significantly over the same period of time is the way that pieces of equipment, not necessarily computers, but other pieces of equipment that people interact with have changed over time. So if we take the washing machine as an example, the odd looking thing in the top left of the slide is a rotary switch that's used for controlling the different machine, the motors and the heaters and the valves in a washing machine. So you had a design where you could select any part of a linear sequence, and the machine could run that as the program that you wanted. So if you wanted pre-wash, you started it at an earlier point in the cycle. But it was very limited in its functionality and also quite expensive. So this is a motor and lots of switches, lots of parts, quite expensive to assemble. So over time, these got replaced by small computers, and I've shown a slightly more up-to-date but not very modern washing machine here as well, that's got an interface to a microcontroller behind it, and that has all the sensors and things that you need to weigh the washing to work out how much water you need. You can sometimes look at the whether the water's clean or not to work out whether you finished rinsing it. So you get extra features as well by adding compute into the equation. Not only do you save the cost by replacing a very expensive bit of machinery, but you get extra features. And moving forward to today, these things now interface to your phone. So your washing machine can, if you get the right one, interface to your phone. So it tells you what program you've selected if you can't read the display on the machine. And I think more usefully, things like fitness trackers, whilst they've got a little display on them, or maybe even a watch, trying to read that on the device itself is quite hard. So by pushing the display information onto a bigger screen, either on your phone or on a web browser, you can actually add a lot of functionality. I think with the home appliances, the gap between moving onto a connected device and adding functionality that people actually find useful is something that hasn't really got through to the designers yet. They're still struggling, I think, with getting the connections to work and claiming that they've got a smart device, even if it isn't something that can give you any added value per se. So my first processor design was about 2003 that I started working on that. Most of the company was designing processors that were going into either mid-range phones or the high-end expensive phones. High-end at that point on a phone meant that you could just about do email, only the keyboards were really small and awkward to use, and you could just about have a website so long as it was text only. So the screen resolution was really limited. The design that was being put into the high-end phones at that time is the same processor that went into the first Raspberry Pi about 8 years later. And if you've ever used one of those, it's not the fastest machine out there. And it kind of does the job, but as a feature phone, it's really quite limited. But whilst the company was designing these, we had a go at breaking into the low end market. So something that would work in a dishwasher. It's a very large market, and there was a fairly well established set of old stable devices that were derivatives of the type of processor that were in the computers from 20 years previously. It's a very cost sensitive market, very low profits, but we set out to build a new design of what the computer would look like, trying to make it as cheap as possible, try to get the performance as good as we could for that type of market, and to try and make it something that, although it might have seemed expensive at the time, would become affordable fairly quickly. So whilst keeping it as small as possible, we were still using the standard 16 32-bit internal registers. So we weren't doing a complete start from scratch. It was something that was supposed to be compatible with the other machines that ARM was designing at the time. As a kind of the reason for having small deterministic machines isn't just to enable your washing machine to do things that it couldn't do before, but also to interact with the real world. So there are quite a lot of applications that require very accurate timing. So not the speed of the processor, but to be able to react to an external event before too much time has passed. So I think probably the most obvious example of this is in the car, the engine management system. It has to detect that the crankshaft has passed a certain point, and then fire the spark plug a few milliseconds after that. And that time window has to be very accurately controlled. It doesn't know how fast the engine is going to turn between one cycle and the next cycle. So it has to wait for an indication of this is where it all is. The machine is here. So you can work out how fast it's turning, and then you have to calculate what the right timing for the spark is. And there's not very much calculation to do. A lot of it is all in lookup tables. It's very, very simple, but you have to get it right. You can't be a couple of seconds late with that. So it's a very different sort of requirement to using a word processor or using a web browser, where if it glitches for a little bit, then it's not going to be a big problem. If you have glitches like that with an engine management or with the motor control in a hard disk drive, things are probably going to break if you get that wrong. So the worst case delay is what matters rather than the maximum throughput. So a lot of the things that are going into computers to make them really, really fast, like caches, branch prediction, that sort of thing, they don't really help in this sort of real-time application where you don't have the flexibility to just be a little bit late some of the time. And although I'm not going to go into any detail, one of the things that the feature that I work on, which is real-time trace, can be used as a way of analyzing well, when the program's running, it's got this much time where it's sitting there doing nothing. You can actually extract that information on a running system to see what sort of margin you've got. Whereas if you wait for the system to get overloaded, you know it's going to stop working, so you can't test it like that. So this design is still relevant today. There are lots of things that it gets used in that didn't exist 18 years ago. Drones that fly themselves and keep stable. That's all done with a small computer, and it's reacting in real time to a few sensors. The fitness trackers, VR headsets with the motion detectors and things like that. The way that your phone can sleep overnight without using a lot of power. There's a very small processor in there, sitting just waiting. Are you moving your phone? If you pick your phone up, then it will wake everything else up, so it's ready by the time you touch it. So there's lots of new designs that have come along in the time since we started this original branch of designs. The original design is still kind of in active use. We've added other variations. So we made a smaller one, we've made more powerful ones, we've made ones with more security features. The original design comes out about 17 times smaller, uses a lot less power, and runs faster. And even that has extended the range of what you can do with it. So although it wasn't really practical when we were designing it 18 years ago, you can now run Wi-Fi or Bluetooth on a processor and have a little bit of extra processing power left over. So that's how these things like smart switches work. It's a device that's running a Wi-Fi interface, and it's got one pin left over to turn the switch on and off. Turning the switch on and off really doesn't take very much extra compute power. Most of the power goes into running the Wi-Fi interface. And the Raspberry Pi Pico, which is the latest new Raspberry Pi device, is a dual-core M0. So that's the derivative that came along after the M3 that I worked on 20 years ago. And one interesting point here is that they're building that on a 40 nanometer process compared with 5 nanometer for the current leading edge. So the scaling factor would be about 50 times smaller if they did use that 5 nanometer technology. But it's quite expensive to do designs on that technology, and it already comes out quite small. It's already 2 square millimeters. If they made that 50 times smaller and then tried cutting the wafer up, they'd spend more of the wafer in saw cuts than actual die. So it doesn't make sense in this instance to shrink it down any further. And the other complication is that the flash memory that they probably have on that device as well, it's not so easy to scale that down. So the constraints that you have between a small cheap device that doesn't have a very high demand on it and a high performance device like you'd have in a modern cutting edge phone or in a tablet or a small computer, the trade-offs pull you in different directions. So just to come back onto the things that I'm considering as I'm working on a design, my interface to a computer really starts with the bus interfaces, not the internals of how the machine works, but how does information get into the design. And on bigger designs, we break it down into blocks that talk to each other over interfaces so that you can separate the timing between the different blocks, because sometimes they can be physically quite a long way apart in relation to the amount of logic that you can get. And the next level down is to start thinking about what are all the registers in the design and how do they fit together. Interesting overloading of the term register. If somebody talks to me about a register, I initially assume that they're talking about a flip-flop. That's a register in my general parlance, but from a software point of view, the registers in a computer are the architectural registers. So these are the registers that you do the arithmetic operations on, or that you write to memory. There's another set of registers that are defined within the computer that handle things like the fault states, whether it's in debug mode, what's going on with exceptions, like where do you take exceptions to, why are you taking an exception, things that control the memory map. So these are all defined as registers in the state. The next level down is also the way that the architecture's state is exposed on the M-class devices as memory mapped registers. So these are locations in memory that you do a store to a location in memory, and it updates some state, or it causes some side effect in a peripheral. And that's kind of the control interface that I'm working with, the peripheral registers that are accessed over some sort of bus interface. And then these connect to a huge network of flip-flops that control the detail interaction of the pipeline or whatever it is that I'm working on. The when I started computer design, I had to learn a new language. Verilog is what we use, and this defines the functionality rather than the discrete and and OR gates that you might think go into a design. So we describe multiplexers, adders, that sort of thing. It's a little bit complicated because every line in the code executes all together. So you have a multiplier and a multiplexer and an adder. They all kind of work on the same state all at the same time. So you have to make sure that the way that they're connected doesn't give you kind of combinatorial loops. It's straightforward once you've got the hang of it, but switching from sequential software to register-based language takes a little while to get your head around. The translation from the Verilog code into gates is mostly automated. It's a very with a big design. It's a very big task, and the majority of that can be automated quite effectively. There's a little bit of very specialist work on placement and constraints to make sure that the tools choose the best way of arranging things, because there's a huge number of different ways that you can arrange even a fairly trivial piece of logic, and it gets mapped into not just kind of 2-input AND gates and 2-input OR gates, but all sorts of weird, wacky combinations of like 3 or 4 input AND gates with OR gates in combinations, things that kind of naturally drop out of the structure of transistors that you need to build up a gate. But that's a whole separate level of the design flow that I don't get involved in at all. It's done. Some of that work is done kind of up front, and then some of the work is done towards the back end of the process to optimize the final performance. You can optimize it for best power or best performance or somewhere in the middle, depending on the application. So some of the things that that vary as you're looking at not just a processor design, but a whole system level design. Over time, the things that cost money change. So 40 years ago, if you wanted a timer to flash a light, maybe if you wanted some relatively sophisticated control over it, you might use a little timer chip, the dedicated analog chip that just needed one capacitor and I think 2 resistors to configure it. That used to be kind of the go-to solution for that sort of problem. Now, that device costs about twice as much for the silicon as a small MCU. If you go for the MCU option, you get 30 other GPIO pins. So that's this type of device. Quite a small device on a board. You can buy these for a few pounds. The Raspberry Pi Pico is the same thing. It's got a lot of functionality. It is timed off a crystal, so the timing is quite accurate, and it's still cheaper than buying a dedicated device and configuring it with a resistor and a capacitor, depending on the time that you need. If you need to count for a day or half a day, trying to do that with an analog circuit is actually quite hard. If you're trying to count higher frequencies, then it's not so challenging to do that in the analog world. And it's not just obvious things like that. Once you've moved into having some of your circuit in a digital domain, it's easier to calibrate it. You can, rather than having to build it so it's right, you build it, you measure it, and you tell it how to adjust itself, and then it just works. So you might have added a slightly more complicated manufacturing process, but you've potentially reduced the cost of whatever it is that you're building by quite a large margin. And you gain the option of adding extra features at the same time. So it's not just replacing an old design with a new design. You save money by doing that, and then you've added extra headroom to add something new. Coming back into the digital, the processor end of things, the old way of designing state machines from kind of 40 years ago might be to have a few discrete flip-flops and an EEPROM, a programmable ROM that gives you a configurable lookup table. So you can build something using a couple of small chips, and it's a fairly standard way of doing design. But and that maps onto the modern equivalent of programmable hardware, the FPGA. So an FPGA is effectively a collection of lookup tables and a collection of flops, and they connect together in configurable ways. But if you're building things in ASIC, the way that the cost functions of building some logic, building some interconnect, building some flip-flops, it's cheap to put a lot of complicated combinatorial logic between two flip-flops, depending on the speed that you're trying to build it to. So the way that you optimize a design for an ASIC or an FPGA gives you different trade-offs. You balance the number of flip-flops and logic gates differently. So you might add extra pipeline stages to make your design faster, because in the grand scheme of things, adding flip-flops might be cheaper than adding extra levels of extra logic. So you restructure the design to fit it into a different timing constraint. As you go to smaller geometries, the logic gates get effectively faster because there's less logic or less capacitance to drive in the gates, but the wires get slower. So you end up having to think differently about how big your design is and how you get signals from one end of the design to the other end of the design. As I showed with the Raspberry Pi, the Pico, the older devices, it makes sense to, newer devices, small cheap devices, makes sense to use older silicon technology. So things don't scale in the same way. So you wouldn't build as complicated a design if you're working with the older technology, because the silicon area does start to cost you more. So you also have trade-offs about are you building a general purpose design, or are you building something that has one job to do and it needs to do it very, very effectively. So you might think there about mining Bitcoin. You can make an ASIC that can only mine Bitcoin. It's a lot faster than even using a GPU to do that sort of thing, but it can only do one job. You have the same sort of equivalence with processors. You have a general purpose processor, or you have a processor that's optimized to be very deterministic. So it has a kind of guaranteed worst case interrupt latency. But that means that it won't be doing things that are massively out of order. Different applications have different requirements. And one of the things that has changed over the time, as we get more capability of testing things, we can afford to build circuits that are more complicated because we've got a better way of proving that they always work. So, and it's the optimization is a very complicated area, but I hope that has given some sort of an idea of how things have moved forward in the last 40 years and how we're still making trade-offs between different cost functions and still building different designs to meet different requirements. So that's it. Open up for the questions.
Thanks for that illuminating talk, Sean. And so it's always interesting to see like how far computing has come. And for me, and I imagine many of our viewers, that's a much lower level view of computing than we normally get the opportunity to see. Am I right in saying that Wi-Fi chip at the start was a ESP8266?
No, no, you're not.
Ah.
No, I carefully selected an ARM-powered one. So this is an RTL00, I think. So this again has the Cortex M3 in it. So this is something that I worked on this design 18 years ago, and this physical one is probably 3 or 4 years old now, but it's still going into current product.
Is that a chip there? One you could use in home projects yourself to learn programming and to build little things, little automations for your home.
It's a Realtek device. So yeah, you can buy these, a couple of pounds each. It's quite useful having a wireless interface on the back of a device. So it means that once you've built it and you've put it in a box or something, you can connect to it and configure it or whatever you want to do without having to connect wires to it again.
Yeah. So I've got a couple of questions here. So the first one is, for someone looking to follow in your footsteps, what learning would you recommend?
So there are a few degree courses that specialize in basic design at this sort of level. It's probably not essential to be on one of those. So I think getting familiar with FPGAs is probably, if you want to get into the hardware side of things, FPGAs is the way to get into it. You can buy an FPGA board for £50 that will run a RISC processor. You can, if you get the right type of board, you can download an ARM core that will run inside that. You can download the M3 and I think the M1 as source code that you can use in your own FPGA. So there's quite a lot that you can do now that wasn't available even 5 years ago to get your hands on not necessarily the inner workings of a computer, but code that runs on a board that you can put your own hardware into.
Sounds really interesting. One more slightly technical question. You talked a bit about the optimization, and I was wondering, is that always done by hand, or is that sometimes supported by software?
So optimization goes from all the way from the microarchitectural design, where you may be making a trade-off as to I've got some area that I can spend. Do I spend that on issuing 2 instructions at a time, or combinations of 3 instructions at a time, or do I spend it on trying to get branch prediction to work better? So that sort of optimization, there's a lot of software modeling that goes into that, building kind of approximate models and running benchmarks to get a good idea of how if I did this, how well would it work? Where's the best place to spend that area? In terms of, I've got a logic design and I want to translate that into gates. Some of it's done manually, so you can maybe make your own judgment about, well, this partitioning might make sense to me, so I'm going to force the tools to go that way, or I'll force it to go the other way by splitting the design up in certain ways. A lot of it can be automated. You just trial and error, Monte Carlo simulation, that sort of thing. So
well,
many ways.
We've had quite a few AI talks on the channel, so I was wondering if you mentioned a technique like that. And okay, so I think that's all for questions. Not sure if there's one coming through just now. There's just one now. If you don't have any physical hardware, are there any software tools that you recommend to get started on with learning the basics?
So there are free simulation tools. I don't use any of them. So some of the FPGA tools, I think, have simulators built in. So that's one thing to look at. You don't necessarily need the hardware to access the free versions of the tools, but there are free simulation tools. It depends where in the design flow you want to get into. So yes, you can do. So all of my work is completely in simulation. I never, in the main tasks that I'm working on, I never see actual hardware. All of my work is completely simulation based, and I'm building both design and working with the test harness. So you need three parts to test a design. You need the design that you've built that's got some purpose. You need something to generate some stimulus to excite it. This can either be kind of something deterministic, like if you've got an adder, then you might just put in all the possible input values, and then you need something to check that the output you get is correct based on what the inputs you gave it. So you need to build all those three parts together, and understanding that and the flows that fit around that is quite a big part of the job.
Another question coming through. What is the single most important development that you have seen in the last 40 years?
I think I might have to say the debug interface that I designed on the M3. So it's not a very big thing, and it didn't replace anything that wasn't possible before, but it's just made the JTAG interface not a 5-pin interface but a 2-pin interface, and that it's not enabled it, but the progression of that whole ecosystem has meant that to test the software that you're running on an embedded device, you no longer have to buy a very expensive emulator. So when I was in my first company, we were using microprocessors to drive some test hardware. You'd have to buy a device that you plugged into your PC that would pretend to be that microprocessor, and to drive the pins, and you could step through the software as it was running. You can do that today in real time using stuff that's built into the processor. So this is the real-time debug and trace and visualization that lets you get inside the processor as it's running without any extra hardware.
Yeah, it does sound like it makes it a lot easier. I'm not expert in that area, so some of that went over the top of my head. But we have one more question. I think this might be the last one. Has your experience at ARM changed since it was sold to the Japanese, and now maybe in NVIDIA? Has it opened any innovative doors that you previously couldn't explore?
I think not for the work that I'm doing. No, it's had almost no effect on me directly.
Okay. Oh, one more. Sorry, one more question. With hardware getting smaller and smaller, where do you see the future?
So certainly there is more hardware kind of everywhere. It's much easier now to put a small processor into something that isn't necessarily even battery powered. You can run a solar powered device or some other form of energy harvesting to get sensors in lots more places. So the Internet of Things has been an awfully long time in the coming, but I think that and there are a few things that make it kind of possible. The compute getting so much smaller and more efficient that you can run it without a power source, networking getting more pervasive. So there are long-range, high-efficiency networking protocols that allow you to connect a device that's miles from anywhere back to the internet, and the ability to do lots of processing in the cloud and to store information and kind of hook into it. So in theory, the heating in my house can see the weather forecast, and it can work out whether it needs to try to keep the house kind of right on the as warm as it needs to be, or whether it can back off slightly because the house is going to warm up in the sunlight anyway. So there's a huge amount of small incremental changes that can go on there, and I think that's probably the most interesting area as far as I'm concerned.
It kind of sounds like it kind of verges on like a control theory and that whole kind of area. Okay, so thanks so much for your time today, Sean. It's been really fascinating. We have our next event, which will be on Tuesday, the 15th of June, where we'll be joined by Dr. Hada Kahid from the University of Wolverhampton, who will be discussing how the Internet of Things can be used to revolutionize business supply chains. More details on that on our website, hearts.bcs.org. And if you've enjoyed this talk today, please make sure that you push the like button and let us know your thoughts in the comments below. If you haven't already, please subscribe to our channel and hit that notification bell icon to be informed about new BCS Hertfordshire content. And look out for more BCS Hertfordshire content coming soon. Thank you very much.